Hello everybody, before we begin, let me introduce briefly. I'm Pablo Gonzalez, PhD candidate from University of Chile. Today I'm going to be talking about our work named Mechanical Properties and Electrical Surface Charge of Microfibrillated Cellulose Imidazole-modified Polyketone Composite Membranes. The presentation has four content. First, an introduction, after development of microfibrillated cellulose membrane and composite membrane. I'll continue by a characterization of the microfibrillated cellulose membrane and composite membrane. To finish, I'll give you some conclusion of this work, future challenge, and acknowledgement. As introduction, hard water is a big problem in the world because this not only affects, for example, industrial and home equipment, but also is associated with a health problems such as atopic dermatitis and calculus. For this reason, today many treatments may be classified as conventional and modern treatments. From the last, membrane technology have a great potential because this has great big advantage such as clean technology, no require chemical solvents, and their efficiency is equal or superior to another methods. However, present disadvantages such as their membranes suffer of biofouling and mechanical damage. For this reason, today it's important to search another material to create membrane with the purpose to treat hard water, in special to removal calcium and magnesium, principal responsible of generate hard water. In the big family of materials that today exist, it's important to mention the biomaterials. And from this, cellulose. Cellulose corresponds to the most abundant in polymer on the planet. This may be extracted from many sources such as vegetal, animal, or bacterial. From a structural and chemical point of view, cellulose consists in a linear polysaccharide whose repeating unit is based on two anhydroglucose rings bonded by glucosidic bond beta 1 to 4. It's important to see that the great presence of hydroxyl group in the cellulose structure because these interact with another chains through hydrogen bonding and in electrostatic interaction. This is important for many applications, for example, in water treatment. Moreover, cellulose is non-toxic, hydrophilic, and renewable origins. Their use goes from powder, particles, and fiber. From this last, cellulosic fibers are structured by microfibrillated cellulose. These are structured by elementary fibrils that have an amorphous regions and crystalline part. In this work, we have obtained microfibrillated cellulose from eucalyptus, a vegetal source, through a mechanical method such as high pressure homogenization to develop a microfibrillated cellulose membrane to treat hard water. But the problem with this membrane is the large size of the pore of this. To overcome this advantage, today exist many forms of modified cellulose. For example, chemical modified through many reactions, but the problem with that modification of microfibrillated cellulose is that require chemical solvent, energetic cost, and environmental damage. Another alternative to this is create composite between microfibrillated cellulose and polymer. Why? Because the polymer offers a great number of functional groups to the microfibrillated cellulose. Moreover, improve the mechanical property of this microfibrillated cellulose membrane. But the problem with that material is that the reuse of this. For this reason, today it's important to search any or other polymers to create composite with microfibrillated cellulose. And there are a big family, exists a polymer who is or have a big interest. And now it's possible to mention to the polyketone. Polyketone is a linear polymer that may be functionalization through many reactions. In this case, through the Palinor reaction. In this work, we use a polyketone modified with a imidazole derivative to create the system or polymer PK15EM8. Now, the question is, what is the new? Well, taking account the great presence of hydroxyl group in the microfibrillated cellulose structure and the great presence of functional group in the polyketone or modified polyketone, it's possible to mixing these through hydrogen bond or electrostatic interaction to create membrane to remove pollutants in water, in this case cations. Moreover, this composite present advantage such as a great number of functional groups and better mechanical properties. Now, who developed this microfibrillated cellulose membrane and composite membrane? Well, we start with a microfibrillated cellulose suspension of 0.5%. After that, this is filtered, vacuum filtered, pressed, hot pressed, and obtained the microfibrillated cellulose, and in this case, we named them C1s. In the case of develop of composite, we use two methods. The first is for impregnation. We taken a microfibrillated cellulose membrane submerged in 10 mm of PK15EM8 solution. After that is pressed, hot pressed, and obtained the membrane called CMP. The second method is for mixing. We mix 30 mm suspension of microfibrillated cellulose membrane more 10 mm of PK15EM8 solution. This is vacuum filter, pressed, hot pressed, and obtain the membrane called CMESC. Well, the optical image show this membrane. In the case of microfibrillated cellulose membrane or C1, this present a white color, and this is due to the raw material. In the case of composite CMP and CMS, this possesses a brown color due to the presence of polyketone. After develop this membrane, properties were obtained, such as thickness, bulk density, and grammage. To characterize this material, we start with the fiber size analysis through atomic force microscopy. In the case of membranes, start with the chemical study through XPS, Fourier transform infrared spectral, the structure and morphology of this material through the field emission scanning electron microscopy, and composition through EDX. The mechanical properties and specific surface area through tensile test and inverse gas chromatography. In the case of electrical surface charge, we use or study through zeta potential. Atomic force microscopy shows the image obtained from the fibers through the high pressure homogenization. From this is possible or was possible to obtain information about their size distribution through the height, wide, and long, and from this was possible to identify that these fibers correspond to the microfibrillated cellulose. The chemical study starts with the XPS survey of the sample. In this, we have obtained signal for carbon, nitrogen, and oxygen for all samples. In the case of C1 or microfibrillated cellulose membrane, this signal corresponds to their structural and chemical structure of this material. However, in the case of composite CMP and CMS, we have obtained the same signal, but the difference with the nitrogen signal is more present a higher intensity to the difference to the C1. To correlate this information, it's possible or was possible to obtain the concentration of the element through the high-resolution analysis of this sample. In the case of composite generated by impregnation and mixing, was possible to demonstrate that the high presence of nitrogen is associated to the presence of polyketone under surface. Now, to study the distribution of pK15 on the surface of the composite, optical and chemical image were obtained. In this, was possible to see that the presence of pK15 is more homogeneous in CMP by the great presence of green pixel, to different to CMS, where it's possible to see a big presence of blue pixel indicating a less presence of polyketone in their surface. To demonstrate this, principal component analysis, or PCA, was made for this sample. In this case, for CMP, it was possible to observe that the gray presence of red pixel indicated a more homogeneous distribution of pK15 and surface to difference to CMS, where there are a more presence of blue pixel. This last indicating that the pK15 there are in the more deeper structure of microfibrillated cellulose. Moreover, through this technique, was possible to obtain the infrared spectra from different areas. In this case, areas where is are white crossed, indicating first the presence of cellulose and the presence of polyketone. From field emission scanning electronic microscopy, was possible to observe the sample. If from this was confirmed that the membrane are structured by a dense network of fibers. Moreover, was possible to observe some pore marked with a wide arrow in this. Moreover, in the composite, it's possible to see that the presence of polyketone does not affect the width of the fibers. On the other hand, EDX analysis showed that the presence of nitrogen in this indicated the presence of polyketone in this material. Finally, a image of transversal cut of this material indicating that these are structured by layers, which implied or permit explain some properties such as mechanical property of these materials. From the tensile test of these materials was possible to obtain the stress strain curve of this, and from this experiment it was possible to obtain information or mechanical properties. In the case of Young modulus, CMP showed possess the higher modulus in this property. In the case of striated failure, CMP and CMS showed values slightly superior to C1. Striated failure does not show a slightly difference between them. In the case of word of fracture, this value indicates that This material presents a mechanism by delamination layer to layer mechanisms. Remember the image of field emissions scanning electron microscopy? And finally, a specific surface area of this material does not be affected by the presence of polyketone. To understand the behavior of this membrane under different conditions, zeta potential were measured. In this was possible to see in the case of C1 that the sample have an isoelectric point EF of 2.4, but to the moment to form the composite CMP and CMES, this changed from 2.4 to 4.2 and 4.5 respectively. This might be due to the presence of pK15 imidazole-18 in this material. Finally, this change of isoelectric point of EF might be associated to the removal mechanism for these materials. Well, conclusion. First, microfibrillated cellulose and imidazole-modified polyketone composite membrane were prepared and characterized. The surface of CMP and CMS were imaged by Fourier transform infrared microscopy. This suggests that a more homogeneous distribution of pK15 imidazole-18 at the surface of microfibrillated cellulose membrane was obtained using solution impregnation method. Tensile tests revealed that CMP possesses significantly higher stiffness than C1 and CMS. Moreover, CMP had a significantly higher tensile strength compared to C1, whereas strain and failure, as well as word of fracture, were similar for all materials. The position of pK15 imidazole-18 on top microfibrillated cellulose was not found to significantly affect specific surface area. The electric surface charge of the microfibrillated cellulose was affected with the presence of pK15 imidazole-18. Composite membranes were found to possess an isoelectric point at pH 4.5. Microfibrillated cellulose membranes were found to possess an isoelectric point at a pH of 2.4. Well, future challenge: develop removal experiment for John using the developed material and study the kinetic and reaction mechanisms. 2. Develop another system of modified chemical polyketone using the Pablo reaction, and develop composite material with the possibility of reuse it. Acknowledgement to Universidad de Chile, University of Groningen, and Universidad Tecnológica Metropolitana, Programma PV. Thanks to Capital Humano Avanzado CONICYT, Becas Chile, grant number 211704775. And thanks for your attention.